Okay, so I'll now run the program on the full data set. So the goal is the same as the 100K data set to evaluate models, to generate similar movies, to train the ALS models. But this time, instead of using the 100K data set, I'm going to use the full data set and using the techniques that I just mentioned in the previous presentation. Okay, so at the documentation, there's a requirements section. I'm going to run the 100K, I'm going to run the full dataset code on AWS, but it's possible to run everything on Windows. Like, so I have a 16 gigabyte memory quad core machine and I could run everything except for a similar database. Except for similar movies database, that took a long time, so I did that on AWS. But everything else I also did on Windows. I have to close all my programs to make things work, but it's possible. If you're running it locally, if you're out of memory, you can use CPU count. This is a command line parameter that's present in many of these scripts. So let's just pick one script, like, you know. And so at the top, I'm going to have a comment section. Well, not this one. Oh, this one doesn't. This one's really fast. So, okay. It's this one. Build title index is very fast. So this is the long, this is the build similar movies database. That's the one that's the most time consuming. So, and this script and also all the scripts have a block of comments at the top that talks about the command line arguments. So there's a CPU count that can be used to reduce the number of threads being spawned. And then so you can use your memory, you can use your computer for other things. So one reason is to reduce the memory usage. The other reason is that if my scripts are using all the CPUs, using all the cores, then the computer becomes very slow and basically useless for, like say reading email. So if you reduce the CPU count, you can still use your computer for other things while the scripts are running. So that's the point. You can run this on Windows, but for the presentation, I'm going to run it on AWS. That's more realistic, I think, to do data analysis on AWS. So to run on AWS, you have to set things up properly, and the AWS instance, it's running Linux and needs to have this Python and these libraries installed. You need to have a C++ library, C++ compiler installed, and upload all the scripts in the Python full data directory. That's the project. So all these scripts. Well, other than the DLL file, because the DLL files is for Windows, but everything gets uploaded. And some of the code is using clustering, and like I said, the clustering is using Amazon's EFS. So this is a file system that needs to be created and then mounted. So I'll go over that also. So now I'll just run this on Amazon and go over these steps in a little bit more, slightly more greater detail. So you need to launch EC2 Instance. Now, I already have the stuff installed in my own images. So, and I'll just show you that I have the stuff installed. I'm not actually going to go over the commands to install them because the commands to install this stuff varies depending on the Linux distribution, because different Linux distributions use different package managers. So that's why the commands are a little bit different. Just find them. These are all very standard packages. But to run the EC2 instance, you select the image, which I already created. And so normally you want to use compute optimized instances, but I'm making a video, so I just want to show what I have. So I want to choose something cheap. So whenever running compute optimized instances, always use spot instances because these are much cheaper, but I'm using a cheap instance already. And if I'm running a standard instance, I can stop the instance. If you're running a spot instance, the instance cannot be stopped. It has to be terminated, or you can take an image of it. So I'll just use standard instance for this one because I'm just showing around. When it comes time for me to do real work, like in the later slides, when I really have to run like these scripts here, I will use a compute instance. Okay, so this is very important. Spot instances are a lot cheaper, and if you need to access like S3, for example, if you need to access other things, you need permissions. So that's what IAM row is. So I usually just create an admin row and I just don't worry about permissions. And I think the next thing to look for is the security groups. I'm using the EFS, so I need my security groups need to have permission to use the EFS, which is this one. Okay, so it's this one. So I need both of these. So this one, the default, gives full access all the ports, all ports, all traffic from this is the local VPC. So default VPC security group. And then this one allows access on port 22, which is for SSH. So I need both of these. Okay, so important have both of these. This one, the first one, is really for using with the EFS. And review and launch. So what I'm using my image. Okay, the images I'm using, this one, it's basically Amazon Linux with this stuff installed. So I'll just go into it and show you that I actually have all that stuff installed. So you get the IP address here. I mean the DNS here. Login as EC2 user. So everything's in the full data directory. I have all the scripts. That's my point. I have data. Okay, so first I gotta show I have all this stuff. So there I have Python 3, 3.7, and NumPy, SciPy, right? So NumPy is there, and SciPy is there, and Boto 3, that's the Amazon library to access Amazon Web Services. That's there, and requests. So make sure these libraries are actually there. And C++, that's the G++ compiler. It's there. It's, you know, but you know, the software is there. All scripts from full data, they're all there. Mount EFS using this, so Linux will automatically mount file systems in that, according to that configuration file. So this line's there. This FS 155B98BD, that's the ID. That's gonna be different for different people. That's my ID. So when you create a file system and then you just follow the instructions on screen, and they're gonna give you this ID. And when we click on this page has instructions on mounting it via the mount command. So for testing you can use this, but in the long term, you want it just automatically there. So in the EFS documentation, elastic file system documentation, mount automatically, they tell you how to do it. They give you the command. That's why I got the command. I'm not good with Linux commands at all. You just look them up as needed. Of course, this ID is different. It's not 1, 2, 3, 4, 5, 7. It's 5, 6, 7, 8. So, yeah. Oh, and make sure that this actually works, of course. Just because you have the commands doesn't mean that it's going to work. So I mounted at full data slash data, full underscore data slash data. So I need to go in data. And I have the movie lens stuff here already in the txt. So, oh, the cluster info.json is from before when I ran my clustering programs. And if I use Control C, like Control C to terminate the cluster server, it's not going to clean up the file. But that's okay. Next time the cluster server starts, it will overwrite this file. So this is okay, having it lying around. A shutdown command to the cluster will clean up this file but it's much more convenient just Control C my way to exit to stop the Linux software. So then when I interrupt the software that way, it's not going to clean it up. So I put the hello.txt in there just so that I know this file system is actually working. Because to save money, you should really delete everything in the file system, right? But if you delete everything, how do you know the file system is working? So you have some basic file there that you can display. Currently, there's only stuff in text. That's the stuff from the movie lens database. So that's all the movie lens stuff. I think I have a command somewhere. Do I have command? Oh, no, down here. Oh, okay, there we go. So if you're not good with Linux commands, here's a command to download. The URL could be wrong, but the wget command to download, and then the unzip command to decompress. And in the beginning, the only requirements that this stuff, the movie lens CSV files, that these files are in the txt directory. All this other stuff gets created as a result of running the data processing scripts, running these scripts. So I think that's me going over the setup for an Amazon EC2 instance. Okay, now I'll talk about building the module, the C++ module for solving the ALS problem. Okay, so notice that when I said upload everything in the full data directory, and this is the Windows, this is the C++ library for Windows, a DLL file. So you need to build that on Linux. And previously in the slide, in the presentation about big data techniques, about multi-threading using C++, I mentioned this already. When I talk about this stuff, I already mentioned how to build it. So here's the command to build it. After building it, the output file will have executable permission. So need to use this to turn off the executable permission so we don't execute it by mistake. And optionally, you can test it. So I'll show this. It's actually already built for me, so there, it's already built. So I'll just run the testing. This is exactly the same stuff, the same output as on Windows. And back here, I did this on Windows. So that's where the file is, the cppls test.py file. It's not in the full data directory, it's in this directory, cpp/python. So back then I did this, but back then it was on Windows. So I'm just, showing that on Linux it's the same thing, but it's using the SO file. That's what's different. So make sure the image has these things. Make sure you can access the EFS. Make sure it has all the script, and make sure it has the C++ least square library, Linux version, so .so. Okay. So far I showed what's on the image, what are the software requirements. Now I want to talk about how to choose an EC2 instance for full data. So go launch instance, and then so I have this software installed. Now choosing compute optimized is usually the cheapest one per computation because they have the least memory. So if you look at general purpose, okay, that's a multiple 4. Okay, so this column is CPU and this column is memory. So this is a multiple 4, right? 8 times 4 is 32. 2 times 4 is 8. 4 times 4 is 16, and so on. So basically, general purpose is 4 gigabytes of memory per CPU, but except for these in the beginning. And compute optimized is 2, right? 4 times 2 is 8. 16 times 2 is 32. So that's why compute optimized is cheaper. It's like a computer, but with less memory installed. So Amazon will charge you less for these computers. So usually compute optimized is what we use. Now, in this software, there is one problem, and this is the only place where it's a problem. This script takes 3 gigabytes per core. So if using 2 gigabytes per core, then just use half the total number of cores. Like I said, there's a CPU count. So this is a script. This is the big script that takes up 3 gigabytes per core, the big bad script. So just use CPU per count to reduce the number of threads being used, and so I can use that. So that's something to keep in mind. So use compute optimized, but when running this script, I need to reduce the number of cores. Okay. Next, once you have chosen compute optimized, you still have a lot of choices here. So, I'll just sort by CPUs and 72, 36. Okay, when you go from 36 to 72, Amazon will double the cost. Amazon will charge you twice as much. There's no savings currently. Okay, there's no savings in going to more CPUs. There's no volume discount or whatever. So the problem right now is that when I go from 36 to 72, I'm being charged twice as much, but the software is not running twice as fast. So the question is like, which one of these do I choose? So, and the answer is to benchmark. And so far, the only benchmark I have is ALS. So here's the least square C++ benchmarks. So it seems to slope off after 9. So the decision is, do you want to go with 9 or do you want to go with 18? So this benchmark is done using 72 cores, the largest instance possible. I think it's 18, yeah. So 18 is benchmark is 275 milliseconds per iteration. That's quite a bit faster than 422. Now it's not twice as fast, right? For twice as fast, this number will have to be 211. So, but it seems to be still good because adding vectors is still faster and multiplying vectors still faster. So So I think I'll use 18 threads. So 18, so 16. There's no 18. We'll just use 16. I think that's a good deal. So 16, you have like, you know, several options. So this is high memory option. This one's gonna charge you more money for it. So not that one. SSD, that's money. So we don't want SSD. So it's these two, I guess. I guess this one. So that's what I'll use for the demo, for the presentation. I also, I left out one thing. Yeah, how do I know this? So how do I know that? I benchmark the memory. Okay. So on Windows, you just, what happens is like I ran on Windows and I just, you know, looked at this graph, but I also have a script benchmarking it. I also did run it on Linux and benchmarking it. So I benchmarked it, you know, on both Windows and Linux. So over here. So full data set, data processing, software layers, memory use, and runtime. So this chart. So software layers, because there's like a common support routines, you know, in these files, and this is the application tasks that I run. So that's the software layer part. Memory use is over here. This one is very little, so just don't bother. No problem. Cluster, well, none of these were originally clustered, but what happens is I wrote the script and it took so long. So on Amazon, it took 22 minutes. This is using a 72 core machine with CPU count set to 18. So it's using a very powerful machine. It still took 22 minutes. So that's when I made this particular one a cluster, so I can add more machines to speed it up. But by default, these are not clustered. So this and this, they're not clustered. They just use multiprocessing. Okay. So this is no problem. This is no problem. This is a problem. So and that's 3 gigabytes per core, is, you know, 18 times 3. You know, it's a 54 gigabytes. It's a little bit less than that. So that's why this one requires more than 2 gigabytes per core. So I have to reduce the core count when running this one. Okay, so there's two sets of things I want to do, right? One thing is to process data, so data processing. The other thing is model evaluation. So I also have memory benchmarks here. It's over here. And on Linux, the memory benchmarks are done by using the peakmem.py script. I wrote that too here, right? Yeah. Memory benchmarks are done by the peak. So that script. No comment here, but okay. Here's a comment. Yeah, don't need a comment if I'm just printing it out for the user. That's why there's no comment. This is the comment. This script tracks peak memory usage by reading the first 2 lines of proc mem info. So I read the first 2 lines of that virtual fake file, in-memory file, and then I extract the memory. I put the memory in the gigabyte format, and I'll print it out. Yeah, I put it in a gigabyte format. The memory is in kilobyte format. So reading from here, the Linux will tell you how many kilobytes of memory is available total and how many kilobytes of memory is available for free. So I use this information, but I put it in a gigabyte format over here. So that's it about choosing an EC2 instance, and also how I got those memory benchmarks and where are those memory benchmarks in the documentation. So alright, next I would like to talk a little bit about basic hardware characteristics. So in this benchmark, when you add more threads, well, at first it seems to be doubling, right? So this is the 4th thread to 9th thread. This, speed is doubling, but then the rate of improvement stops. It's no longer doubling. It's still getting faster though. And then you have these other situations where adding more threads actually increase the time, the execution time. So it's actually slower and slower as more threads are added. So, and the reasons for this is very complex, a lot of variables. The CPU is very complex, but there are 2 general principles I would like to talk about, and that can explain a lot of these things. So the first principle is that the CPU, and it's like a chip. So this green box represents the CPU, and the CPU has their own internal memory, and the CPU is running at full speed only when using its own internal memory. So this is like CPU adding 2 numbers and then storing the number like somewhere in the internal memory. But eventually the CPU has to move the data to the real memory out here and move the memory in here. So as more CPUs are added, as more threads are added, they're activating the CPUs. So when I'm using 9 threads on a 72 core machine, those other CPUs are basically idle. So as I utilize more and more CPUs, the memory can't keep up, and that's why the rate of improvement slows and eventually stops, because the CPU requires data from the real memory. So the orange line here cannot keep up with the green internal lines, and so that's one explanation of why the rate of improvement drops as I add more threads. But that does not explain why, in some situations, adding more threads is actually harmful. So there's another principle of what's going on. The memory that we're using, the DIMMs, we cannot read 1 byte of memory from them at a time. We have to read a whole bunch of bytes. So exactly how many of that, it could be 500 bytes, could be 1,000 bytes. So let me say that suppose I want byte number 5 out of DIMM. I can't just want 5. I want 5, but I can't just read 5 from it. So I have to end up reading, say, 0 to 999. Right. And then suppose that next I want to read byte number 1005. So I can't read just 1005, right? I want 1005, but I can't get that. I have to get the whole bunch. I have to do that. Now, suppose that this CPU is 2 threads. So 1 thread gets this block of memory, the other thread gets the upper block of memory. So that 1 thread then uses 6. And this block happens to be inside the CPU on chip cache memory already. So when, let me say, so you need a 5, then you want a 1005, then you want a 6. So in this situation, when I want a 6, this is already there, so I just get the 6 right here. Right, so this is 2 threads per CPU scenario. Now suppose I increase the number of threads to 4, okay? So there are 4 threads in the CPU now. Now each thread, it gets less on cache memory. So that 1 thread needs a 5, so okay, so 999. And the thread needs 1005, so they have to move this out and then bring in 1000 to 1099 to get to read 1005. And now the CPU needs 6, so then this has to go out. They have to write this to the main memory and then bring in 0 through 99999. So as you can see that if I have a lot of threads, each thread gets a smaller and smaller portion of the CPU on chip memory, I'm actually doing more data transfer. Like before, I have this block lying around, so I don't have to do a data transfer. But now, because I have more threads and I only have one cell for that thread, I have to redo this transfer again. So that's the situation where at some point, if you add a lot of threads, and in certain memory access pattern situations, additional number of threads can greatly increase the number of memory transfers, and the whole CPU is just waiting for these memory transfers. And that's what I think is happening here. That this kind of operation requires more memory transfers, and actually more threads, which actually just slowing it down more and more and more. The CPU is just waiting for that orange line memory transfer. So that's my attempt to provide a very simplified, big idea explanation of what's going on in some of these situations where adding more CPU eventually, adding more threads eventually just make things even worse than before. So now do model evaluation on the full movie lens dataset using AWS. Oh, these models are the non-ALS model, so median prediction, tag count, and the tag LS, tag least square models. My plan is to just run these commands on AWS, and then I'll talk a little bit about the software. So like I said before, I'll use the 16 CPU instance. Be sure to use spot instance, very important, it's a lot cheaper. Probably not necessary, but that's my habit in case I ever need to use S3. Those two. So I want to show that in the beginning, there's only the txt directory. There's no other directory. Txt has the CSV files from Movie Lens. So as I run the scripts, it's gonna create files in in and out, and also ALS directories. So the first command is the randomized training set. So the data set, so currently the data is in the CSV file, and I need to break that data into a training set and a test set. And the training set is generated randomly. So every time I run this command, randomized training set, the training data will change. But you need sudo because the EFS is considered like, it's not considered to belong to me. So I need sudo to have permission to access the EFS. And I'll just put the recording on pause until this is done. Okay, so the data processing finished after about 1 minute and 47 seconds. So it reads the CSV file, movie CSV, and it's create these bin files. So this one takes, so this is the time, right? So This one takes a long time. The ratings file, the 27 million ratings. And after I get the ratings, I save as user ratings.bin. So user ratings.bin, I'll show you that in the documentation. So it's user ratings.bin. So it's a list, and each list is a user ID followed by another list, nested list of movie ID and rating. So that's the user ratings.bin. That's the big one. That's the 39-second, the one of the 27 million ratings. So all these they don't change because it seems like the movie lens database is only updated like once a year or something. So this is like a one-time thing. So this is where it starts to do the training and testing sets. User ratings train, user ratings test, and movie medians train. Right, so every time I generate a training set, the medians must be drawn from the training set to be sure. So every time I do a training set, the movie medians has to be recalculated. Show you so user ratings train, user ratings test, right? So in the documentation there, user ratings train, it's a list. Each item in the list is a user ID, and for that user ID, I have another list of movie IDs and ratings. So that's the data structures. Notice there's a lot of lists. If you go back to the code in 100K dataset, there's a lot more dictionaries, but it's easier to split up a list to multiple processors and computers than it is to split up a dictionary. Although it's possible to split up a dictionary, but splitting a list is easier. So there's a preference for lists. Again, let me run this a second time, because one of my point is that all this is like one-time processing. So I'm running it a second time. So now the data processing is done for the second time. So it's the same files. User ratings train, user ratings test. Now all this other stuff is constant, so they're not being regenerated. In particular, notice that I started reading user ratings bin at 0, and I'm done by 8. So this reading in the user ratings.bin took 8 seconds only, but when I'm extracting it from the CSV file from here to here, it took 36 seconds. So about 4.5 times faster. So that's why it's important to save these things as a binary file, save the variables as a binary file, and then just use Pickle to pull it back out. It's a lot faster than getting it from the CSV file. So now so next thing I'll do is run the model evaluation. Okay, over here. So I did this. I did it 2 times. So next I run this. So this part of the project is I use the cluster computing technique, but it turned out to be not necessary. But I didn't know when I was writing it. I didn't know how fast it is. So it turned out that this is not really necessary, but because it runs so quickly. So first thing is the cluster server. It's been started here. So I'll start more windows. I'm running everything on the same computer, so because I know it's not that. So second one, I'll run the worker server here. Second one. Okay, I need to go into right directory. Oops. and the first one should see that join with 16 CPUs. And the third one, well, I'll just do the median predictor. They're all the same. Yeah, I had the wrong IP host name. So okay, I need to be in the right directory. So here it's starting to work. It's doing the setup, you know, get ready to do median eval, and then a bunch of median eval, and it's very fast. So a cluster is not really necessary, but I already wrote the code, so it's doing a lot of evaluations per second. So it's doing all. So there's like a 230,000 users, 6 seconds. It did all that in 6 seconds. So it's a lot of users being done per second. The other, it prints out the result here. Now, when I run this on Windows, I'm running this on Linux right now, obviously. But when I run this on Windows, I'll also give a bar chart. I'll bring that up. It looks like this. Not very good. A bunch of people who like total failure to predict, and it's a bunch to do with that. I think this is because of when I'm using the full data set, there's a lot more people with relatively few reviews. Remember that only 20% of the data is being used for testing, 80% is for training. So if a user has 40 movie reviews, which is quite a bit, that's a lot more than what I have over here. I mean, right? So it's a lot more than what I have in my testing code. This is not 30. Okay, so if you have like 30 movie reviews, but I'm only using 80% of that. I mean, I'm only using 20% of that for testing. So that's just 6 reviews for testing purpose. And like I said before, the metric, when you have 6 reviews, something like this, you're either 66% rank agreement or you're 100% rank agreement. If I move this over here, that's 100%. So that's why, you know, I think that's why there's this bunch of people with, you know, perfect prediction. And the median's not that good. So that's why it has a bunch of zeros. Let me run another one. This is the longer one. Let's see if it... Right, because I did my benchmark. So when I did my benchmark... Yeah, I did my benchmark on the 18 CPU on the 72 core machine over here, 72 core. So I'm just curious. Like this tag. And this is the one that took the longest out of these guys. 91 seconds. So I'm gonna skip this one, but it's the same thing. You get the same. You get an average number, and if you're running on Windows, you get the bar chart. I'll just bring that up. It looks like this. So a lot better than median, because median had a really high bar over here, and this is tag least squares. And I'll jump over results. So okay, so it gives you an estimate, and you know, yeah. So if you can't wait, you can bring in more computers. This is cluster mode, so Out of all these model evaluations, this is the longest one, so this is the only one that can really benefit from running multiple computers. I'll just jump straight to the evaluation results. So, okay, full data. I have the results already, so I already read it before. So tag least square did a lot worse than before, and ALS did a lot better than before. It's kind of expected. There's a lot more data for ALS and tag least squares, and also tag counting. They don't really benefit from more data. What they need is more data per user, and there's actually less data per user. On a per user basis, this data set has more data. On a per user, it's fewer ratings, but it's a lot fewer users. It's like 600 users for 100K ratings. So let's compare it. So this one's the same, 62.5%. Where's this? Oh, over here. Okay. So it used to be a little bit higher, but there's less data per user, like I said. So that's kind of expected, sort of expected. ALS is more about total amount of data, so these all went up. And I'm not totally expecting that, though. But I still like that. I still like the tag least squares, because out of the models I made for this project, this one has the fewest number of parameters, and so it's the easiest one to understand. And you just heard the ding sound. Oh, that's because on all my scripts, at the end of my scripts, I put a /a, the bell alarm. So, which I just ran this. I just ran this one. So at the very end, I always put this /a so you can just hear it, because these things do take a while to run. Okay, so like I said, 62%, right? Which is what I had over here. Okay, something here. Yeah, so 60, 62, 60, that 62, 61.9. Oh, no, exactly, excuse me. So let me zoom this out. Okay, so it's this one, 62.5% exactly. It's very, very stable for tag LS and tag count. See, ALS is the one that has sort of a range to it, but these two, are really stable. So that's that. And this one's with the less than 5% and greater than 95% with those data removed. So that one is if I remove this data and I remove this data, the two peaks, then the ranking will be 61.9%, a little bit lower, and that's kind of expected because where's that picture? Got rid of it. Okay, that's kind of expected because there's a lot less of this. There's a lot more of this over here. So if I take out those, the average kind of goes down a little bit. So I think I'm done running this. Oh, just one last thing. Yeah, so it took 169 seconds. So the benchmark was over here. It was 91 seconds. So 72 core, 18 CPU count, 91 seconds. Yeah, but what I'm using now is a lot cheaper. What I'm using now is 4 times cheaper. So I'm taking almost twice as long, but my instance is 4 times cheaper. So it's a good deal. So I'm done with that, and always want to get rid of this. Terminate always. Yeah, because you can't stop. Okay, how to do. realized, okay, so there was no stopping option. That's the weakness of the on a spot instance, because I cannot stop it. So I think, like I said, I'll run these first, and I'll talk a little bit about the code, these scripts. So randomized training pi. So first thing is that not everything is multi-threaded or multi-processing. So multi-processing for repeated data generation tasks only. So there's this one-time generation task, and there's no multi-processing, because writing multi-processing code takes a lot more effort. And if it's a one-time thing, just don't bother, because like I showed, loading data from the variables, loading a variable from a hard drive using Pickle is very fast. So loading the ratings is only 8 seconds, and that's by far the largest data structure. So data processing, it's a bunch of scripts. These are application level scripts. So this is one that I just ran, randomized training set. And these application scripts depend on these common support routines down here. And in the documentation down here, movie lens data.py, that has a chart that shows you like this function requires this file and produces this bin. So it has a chart, and these are one-time binary files, and I separate into multi. These are repeatedly generated files, and so these functions, MP suffix means the functions using multiprocessing, and multiprocessing means that proc file, that underscore proc file, is being used to support this function. There's a call tree. Some of these routines are pretty long. Okay, so this is one I just ran, refresh training set. That's the default ratio. If you don't want 80%, you have to change it here, or change the number that's being passed in. So this one's pretty long. This one's for ALS. So just to show that there's a call tree for this one. Hopefully it's helpful if you ever need to dive into that function. So go over a little bit about this one. So structurally, it's a big file. It's 700 lines. Structurally, it's very similar to the basics / multiprocessing add.proc file. So I think it's important to understand this basic example. It's a lot shorter, but the concepts are the same. So I have a function that sent data to the interpreter. So this one sends the same data. This same data is sent to all 4 interpreters. A function that splits the data structure up and sends it to the interpreters. I call them processes. And there's one function to split things up. There's 2 functions, multiply and add, in the basic example. And then there's one function that merge results together. So if you look at the movie lens underscore data proc, it's the same concept, but more functions. So there's 1 and 2, there's 2 ways to split things up. There's a lot more functions that are run on the interpreters, right? So you split the data, run something on the interpreters, and then you merge the data together. And there's a lot of merge, right? Before, there's only one function, concatenate variable into list. I still have that. It's just that I have concatenate append variable into list. So append is different from concatenate, right? Concatenate is the plus sign, and append is the dot append function. But these are very similar. It's just instead of adding, I have a dot append, and this is a NumPy array. So concatenating, but for NumPy arrays, updating into set. So there's more functions, a lot more functions for merging data together. But the concept is the same. You have to split the data up to interpreters. You have to run all these functions on the data, on each interpreter and then you merge them together. So it's very important to understand the basics before trying to understand this file. That's what I'm trying to say. Yeah, so go over the model evaluation code. I'll go over this one. They're all very similar, all three of these. So I'll do here. So I only talk about the median because they're all very similar. So understanding the median, this one, understanding the median predictor.py, that's the key. That's the easiest one. Over here. So I'm sending an operation. Well, the name of the operation is distribute, but distribute is sent to the cluster. So what gets passed on to the worker server is the median eval. And median eval then translates into median setup. Like, remember the worker server is a state machine. It has a setup and it has an eval. So I still have it. Okay. I close the connection, but I can still see the stuff, right? Yeah, so you can see this median eval setup, tell the worker server get ready to evaluate, and then, run the median evals. And later on, when I ran the tag ALS, it's the same thing. Tag ALS setup, eval setup, and then the actual eval command follows a bunch of eval commands. So it's the same pattern as before. One thing's different is there's a model interface. Yeah, so where's this? Well, I was talking about the median, so let me use that one. Oh, the median doesn't have one because it's too simple. Oh, this one has it. Okay. Okay, so this is one thing that you can't use the median on. So previously in the basics, in the 100K dataset, all these files are completely independent. So there's a bunch of duplicate code. Now these models, they all inherit from this model. See if I can go there. And this is just an interface. So all the models I use have a predict function. The predict function takes a movie ID. They will try to predict it, predict a rating. So return none if no prediction can be made, maybe not enough information or whatever. So they're allowed to return none for if unable to make a prediction. So tag ALS predictor user profile follows this interface. And median doesn't, because median is just looking up to median in a dictionary, so there's no model really. Yeah, there's just a main function. And the other one also has a tag count predictor, which I didn't run, but it's, yeah, so there's a model. Go there. There's a model and follows the model interface, and then it has the predict function here. So that's me going over the doing model evaluation, evaluating the median, tag count, and tag ALS models using the full data set, the full 27 million ratings data set. Okay, so now I'll run the ALS model evaluation. I won't run the model evaluation. I'll just run the data processing portion. I'll just run this, because this part is the same thing. It looks the same. Okay. So the data processing now is done, and it's 3 minutes 23 seconds. Previously I ran the script that creates a training set already, so the user ratings is being read directly from the hard drive is not being extracted from the CSV file. That's why this part is shorter. So if I run this whole thing from scratch, it would take longer than this. Okay. So it's like before, I have to do user ratings training and user ratings test. So I go through each user, I split the data 80% into training, 20% to testing. This is the same as previously. What's new with ALS? Well, okay, this is new with ALS. I have to shrink the data. So ALS has a requirement, right? Right, because the least square procedure is stable only if you have sufficient number of linear equations. So I explain here, I'll kind of repeat this. For a model using 3 factors for movies and 4 factors for users. Users have an extra user bias factor. The movies can be included in the model only if it has been reviewed at least 3 times, and the user can be included only if he has made 4 reviews. So ALS is like an exclusive club to qualify to be included in the ALS 3 model. These people have to make 4 reviews, and these movies have to have at least 3 rate users. And these users have to be in this pool. So it's kind of like an iterative procedure. So previously in the 100K dataset, I did shrink the dataset, but I did not print how many users and how many movies, because back then the users have a lot of reviews. It's 100K reviews, and they had like 600 users. So basically all the users got accepted into the ALS club. But in this case, with a full data set, no, there's a bunch of users who got rejected, and there are movies who got rejected. A lot of movies got rejected. As we go from ALS 3 to ALS 11. So this table tells us how many movies are in the ALS, are encompassed by the ALS model. So when I make recommendations, I'll just do this. Oh, I'm at the top already. So when I use ALS 11, okay, those recommendations are restricted to 20,000 movies. So there's a bunch of movies that are not going to be recommended by the ALS 11 engine. So that took a while, shrinking the ALS dataset, 55, slightly over a minute 20 seconds. Then I start building the ALS model. Now, from a benchmark, it's already known that 18 threads is the fastest for least square. I did the benchmark using the 72 core machine. And it's known that this is the default algorithm 1, 18 threads is the best. And I had other benchmark. I think here, data processing. Okay, here. Total time of 240, but I also wrote down. Okay, the ALS training time can vary due to the use of random starting vector. The ALS training time is between 54 seconds and 1 minute 50 seconds. So over here, so ALS started here, and training's done over here. Okay, so total, okay. Oh, okay, I see. So this is when it's finished, but I have to save these to disk, and that took an additional 3 seconds. Or that's the same thing. That's the same thing, okay. So anyways, it took 1 minute and 6 seconds. So which is why benchmarking is important. Like this set is 54 seconds to 1 minute 50 seconds, depending on luck, basically. And this is done using a 72 core machine. But the thread count's locked at 18 because I already know from previous experience that 18 is the best. So this shows the importance of benchmark. I'm using a machine that's like 4 times cheaper because it has 16 cores as opposed to 72 cores, more than 4 times cheaper. But I'm getting the same running time for ALS because I previously benchmarked it, and that's the best thread count. Okay. So that's my comments on the train ALS model script. So this is a little bit different from before. I'm not going to run this because this part is exactly the same as before. This part is a little bit different from before. The files are in the ALS directory. Let's just go there and oh, it's in the data directory. See, originally it's just a text directory, but now it's got all this other stuff. So every sorted by name. So ALS 2 files here and a bunch more here. So every ALS model has a set of files, and this includes a model. So before, in the last slide, when I did the data processing for these models, the data processing is just generating the test set and the training set. So that data processing is just this stuff and this stuff. Yeah, the median train. In the previous slide, the models get created when I actually run the predictor. So for every user, this script is creating a model for that user, and then based on the user's training data, and then testing the model using the test data. So the model creation is down here, but with the ALS, the model creation is here because the model creation requires all the data. So that's the difference. And the models are over here. I have documentation on what these things are. So as a review, ALS model there's a user factor and a movie factor, and then to apply the model, we pick the right user based on which user we're talking about, and pick the right movie based on what movie we're talking about, and then we just do this equation to create a prediction. So the ALS model is basically a bunch of user factors and a bunch of movie factors. So input output data, ALS data. So I have example for ALS 3. Oh, okay. Here's the ALS model down here. A NumPy array of item factors and a NumPy array of user factors. So those two are the ALS models. So this application here, the one doing this, all these recommendations, this application is using the item factors. The user factor is me. So the user factors, oh, can you scroll down? The user factors down here. That's me. So the user factors are not necessary. Only the item factor is necessary for the application, for the prediction application. The user factor is necessary for this part, the ALS predictor part. So what else is there? Oh, like I said, the ALS is like an exclusive club. So they have their own set of movie IDs and their own set of user IDs because all these people got dropped out because they don't have enough ratings. So a bunch of people, some people, not that many people, but a lot of movies got dropped out. Right, and then you have to have a test and train. So testing set and training set for each one, right? Because each ALS model has their own pool of users. So they all have different training sets and test sets. That's why there's there's this file, train and train and test. That's why. And that's it. That's it for ALS model. And running this is really fast. Instead of running, I'll just show the benchmark. Model evaluation, it's like 5 seconds or something. Yeah, it's 25 seconds, but there's 5 models, right? Right, there's 3. Yeah, there's 3, 5, 7, 9, and 11, totaling 5 models here. So it's much faster than the other ones because these two guys, count predictor, tag count, and tag ALS, they're creating models for each user. And ALS is just applying the item factor and the user factor. ALS is just applying the user factors and item factors. So that's all I would like to, that's my comment on the ALS model evaluation. So previously I ran the train ALS models.py to train ALS models, but that was for model evaluation. So the previous code trained ALS models, but with 80% of the data. The remaining 20% of the data is for model evaluation. So now I have to redo this train ALS models, but with the training set ratio set to 1. So to create ALS model files using the full data set, the reason is that the final application uses ALS as a prediction algorithm, so as a recommendation algorithm. So to get the best models possible, use all of the data set. So this command is the same as before, except that now I have to set the training set ratio to 1. So here's the command. I just ran it. And compared to before, there are more movies because there are more data is being used. So both more users and more movies will be accepted into the ALS club, so to speak. The outputs are in the ALS directory. Let me just go there. Okay. So before there was a testing. So before, and now it's just training. So you see like user ratings train, but you don't see user ratings test anymore because everything goes into the training set. Okay. The files are needed. Okay, so there's a set of files for each ALS model, but you only need 2 of them for the application: the item factors and the movie IDs. The item factors is here's a prediction equation. The item factors, the M0, M1, M2. It's the M's. And the movie IDs tells where to look. So all the item factors are stored in as a single vector. Here. Yeah, the item factors it's a single NumPy array, and the movie IDs will map from the standard movie ID to the zero-based movie ID, which is that's the movie ID used by the ALS algorithm. So those 2 files are needed for the application, and you need to manually copy the files to the application. Because right now I'm not using a special naming convention. So this file, user ratings _ train, it could be from this run, which is using the training set ratio equals 1, which is using all of the data for training, or it could be from the previous command that doesn't have this part. So the previous command produced the same file with the same name, well, a different file, okay, different content, but it has the same name, and that one is only using 80% of the data. So right now I'm not giving that file a special name, so it's important to just manually copy the file over to the application. I want to point out the medians do get a special name. So the median is in the, I think in the out directory. It's either that or in the, okay. Actually, I should look in the documentation myself. I don't remember. Yeah, it's in the in directory. There's a medians full and there's a medians train. So the medians train will be using 80% or whatever the training set or whatever, you know, training set ratio is. Whatever training set ratio is here. So it's in the in, right? So ALS what is it? Oh, movie medians. There. Okay. So there's a movie medians full and a movie medians train. And the movie medians train is using whatever training set ratio. That's not 1. That's it defaults to 80%, but you can modify it here. And the medians full is using training set ratio equals 1. So with this naming convention, I know which one is the one for the full data set, for the full, that's being trained using the full data set. But for ALS currently, I did not give them special names. I did remove the underscore test.bin though, but I did not, currently I don't assign special names. So that's why this step is necessary to manually copy the files over. So that's how to get the item factors and movie factors file for the ALS full data set. So now I'll go over how to build the similar movies.bin file. So first of all, the meaning of this file. Full dataset project, input output files. There. So this file maps from a movie ID. It's a dictionary, the brace. And it maps from a movie ID to a list of similar movie IDs. So in the application, when I click the link similar, and it shows these other movies, it's not computing the similar movies in real time. It's loading from a previously determined set of movies. It's loading from this a dictionary that's loaded from this binary file. So previously the cluster mode has been unnecessary. Go this. But this time it is necessary. So previously I was using cluster computing for evaluating models, and at most it's 91 seconds. That's really not, you don't really need a cluster to do that. This is a single computer. Just use a single computer. This time using a 72 core machine with 18 CPU. It still takes 22 minutes. So this situation, I'm gonna bring up more computers to help me finish the job faster. This file, similar movies, build similar movies, DB, was actually originally written as using just multiprocessing only, using the proc, movie lens data proc for support. And it's only after I try to actually run it on my computer and discovering how long it takes that I modify the file to use cluster computing. But it's still possible to run this file in a single computer mode. So I think it's down here. Yeah. So it goes to the main function, it does a bunch of processing, and then down here it tries to look for the cluster info JSON file, and if it finds that cluster info JSON file, it's going to build a cluster. But if there's no cluster information, meaning this code cannot find the JSON file for the cluster, it's just going to build locally. And when you use build locally, it uses the proc, which is this one for support. And it's using find similar movies. The find similar movies function. Okay, so when using the multiprocessing, I don't have workflow control. That means I don't have an estimate of how long things take. So what happens here is that I'm gonna process 200 movies, and then I'll print out like an estimated completion time. And this happens once per thread. So on my computer, on a quad-core computer, this estimate will be printed out 4 times, and the real estimate is the latest of those 4 estimates. This script will, if running on a local computer, this script will take a long time, and it uses 3 gigabytes per core. So to reduce the memory use, and also to reduce the impact on the computer, so you can use the computer for other things, you can use the CPU count flag to reduce the number of threads. So for me, by default, I have a quad-core computer, so by default, this will be 4 for me. So I can reduce it to 3. So I can still do some things with my computer while the script is running. But in this presentation, I'll run this on AWS and summon up more computer nodes to finish the calculation rapidly. So I have login here. Let me show you this. So right now I have a micro instance as the cluster server. Well, that's the intention. But I just logged in. I want to show the startup script. I have a startup script here called startup. And this startup script will go into the full data directory, and then it will run the worker server program. So previously I've been SSH in to the EC2 instance and then manually running this command. So because this time around I need to do this on a large number of computers, so I'm doing this via a startup script. And that's a startup script here. Okay, so now I'll run the cluster server. So the first command, run the cluster server. And previously I've been using just one computer for everything, but this time it's a real cluster. So the cluster server should be something small, something cheap. It does some work, but it doesn't do that much work. So I have to go into that directory. So that's the cluster server. Now this time around I'm not going to manually start up the okay, so now I'm going to launch. So next step is launch the worker server. This time before I do that, I need to, because I will be running a larger number of computers this time, so it's good to check your limits to see how many computers you can run. And I want to point out that people all want the newer machines. So the latest generation, okay, I need 3 gigabytes per core. So I could do something like this, reduce the CPU count to free up enough memory, or I'm just going to get a larger instance. So the C5, wait, let me do instance type here. Okay, it's the M5. So compute optimized instances have 2 gigabytes per core, but general purpose, which is the one I'm looking at, general purpose has 4 gigabytes per core. General purpose has M4 and M5. M5 being the newer machine now. M5, so M5 4x large. So over here I'm looking at the limits. So Amazon imposes limits on how many machines I can run. You can always request a limit increase, but that's not necessary. So if you look at M5, if I use M5 for X large, I get 5. However, if I use M4 for X large, so same thing, I get 10. And the only difference being it's the same 16 CPU, 64 gigabyte memory is the same loadout, but M4 being a preview, the earlier generation of, or Haswell, older machines basically, that's M4. But I do get 10, so I'm just gonna go with the M4 actually. Okay, so I'm gonna launch instance. I have one running. I have that's a cluster server. I'm gonna run more. General purpose, and I guess it's easier just pick it from this list, right? Well, why not the larger one? Because they have more limitations, and also, like I said, more threads, the performance decreases on a per thread basis in general. So you don't want these anyways, but also because they have more limitations. By that I mean the limits column. This column they won't even let you. Right, so if you go to 12x, there's only one instance. You go to 24x, it's 0. It's just not allowed. 16x, 10x. So I can have 10 of these, but only 5 of those. Okay. So I'm gonna go with the M4, 4x large. Launch instance, my AMIs, general purpose, M4 4x large. Very important to spot instances are a lot cheaper. This is just a habit. I actually don't need it here, but I always do it. So now this is new. This user data, that's the initialization data. So instead of using SSH to log in and manually run this command, I'm just gonna have it run this starting script, and then it will run the startup script I just showed right here. CD full data. Okay, and you need all of this. So you need this. Without this, it doesn't work. It's not default. This you need it because it does not start in the home directory. So you need to CD into your home directory. And this is the startup script that will trigger the worker server.py file. And security group, same thing. Did those two. Now, unlike before, I should be able to just watch this and they'll say a worker server has joined. So eventually this will say worker server joined with 16 CPUs, right? So a new worker node joined with 16 CPUs. So now I have a cluster of one server and one worker. I'll go in there, and I do need to go in there to run the similar movies script. So okay, so get the IP, get the DNS. And then let me go to the data and just remove everything and just start over again. So, well, okay, ALS in, out, temp out, just remove everything except for the original movie lens files in txt. And I'll just rerun this over again. So the first one, this one is the cluster server, and this one is the worker. Oh wait, it's not this one. I have to go back out to the full data. Okay, this one. Just make it large. And before it goes into cluster mode to do the similar movies calculation, it's gonna have to reprocess all this stuff. So the code has processed a bunch of things, and it's now starting to build the database of similar movies. Oh, it takes a long time. It's okay. So it has to read in the movie CSV because I deleted everything. So a lot of these bin files, genre count, movie ratings have to be recreated. And one of the things I had to do in the 100K ratings, the more basic example, I have to calculate these manually, but this is not now calculated automatically. There's no buff limit though, but it works. So movie similar to Star Wars, it's this stuff. So that's the criteria. I have to tune the algorithm such that when I search for Star Wars Empire Strikes Back, the most similar movies, the top 2 has to include the Return of the Jedi. So it's running this about 46 minutes more. So this is the part where I start more computers to help out because this is taking a long time. 43 minutes. The estimate is kind of uneven because some similar movie calculations are easier than others. So sometimes it's going to be a little bit faster. Sometimes it slows down a little bit more. It's not like the example where I add 2 vectors and every single addition takes the exact same amount of time. Now some movies are faster. Basically, the more reviewers they have, like this one had a lot of reviewers. The more reviewers they have, the longer it takes to calculate the cosine similarity value. Okay, so I'll just start more servers to help out. So it's this stuff. I already did it on one server, so I know it works. So launch instances and same stuff. It's that one. Yeah, 64 gigs. Well, 4 gigabytes per core. That's what's important. Spot instances. Okay, so I launched 1 already, so I can do 9 more because previously I went to the limits page, I saw 10, so I can do 9 more. So that's the new part. The start script is to trigger the startup. Oh, my habit is always give myself admin role for IAM, whether I need it or not. And that's it. Oh, they're all fulfilled. It's gonna get more and more and more. It's 4, but it's just more and more. So this is a cluster server. So eventually when I go terminate it, I'm gonna terminate everything except for this one. So you see the computers are joining. Every computer is bringing 16 CPUs. And this is still 41 seconds, but as new computers join and help out, this number will drop very quickly. So this is normal. So even though they joined, it takes a while for them to actually assign work, for them to start offloading the operation, because they have a setup stage. So the worker server.py, first it goes into the setup stage, and then it goes into the working stage. So there's a pause here. Oh. So after joining, there's a pause. And now they're starting to take more work. So now the time is greatly reduced down to just 5 minutes. Okay, so I turn on the recording again. This is in the last 20 seconds or so. Let's see if the estimation algorithm's good. Is this really the last? Oh, is this really the last 10 seconds? So I think it is. So after this hits 0, it's merged. It has all these temporary files, and then it's merging all the temporary files together. And that's now you hit the alarm sound, the /a, the print /a command. So this is done now. So the first thing is just turn them all off because they're costing money. So I think that all of them, yeah. So don't turn this one off. That's what I'm gonna use to look at file. So this one got closed. So I just use Control-C. Okay, oh, data, and then it's in the out. So it's in similar movies. So that's a file. So what I could try to do is try to read this file and see if it has stuff in it. You know, it's a quick check to see if the file is correct. So similar movies, it's a dictionary where there's one ID leading to a list of IDs. I can check using my application too. So Python 3, F equals open. So similar movies.bin. The mode is going to be read the binary. Think. Oh, I need pickle. And S will be similar movies, and I'm going to use pickle. I think it's .load. So type S. Okay, so it's a dictionary. And I have the application running here. So, oh, I have to start check. What if this tells me? Well, I could look at the ID in the code. I'm gonna just bring up the actual data. So I'm just gonna find ID this way. Okay, so Star Trek II, okay. 1374. So S 1374. So movie similar to ID 1374 includes 1376. And that's Star Trek 4 Voyager Home. So this one, Star Trek 4 Voyager Home. And next one is 1356. So that's Star Trek First Contact. Here we have here First Contact. So okay, so I think I have the right file. So that's how you build the similar movies .bin file, and how you can immediately check the movie IDs, see if they make sense. There are two more files needed by the application, the title search index and TMDB data. Both of these scripts don't require much processing power, so I think it's best to just run them locally. And here's one of them. Build title search index. So the 100K version, I had another version, a simpler version here. It's almost the same thing, but this time around, there's no file redirect. This script is already saving the output in this text file, because that's to avoid having Python printing out foreign characters, which might crash Python. And the second one needs more explanation. This one, TMDB data. First of all, what is the TMDB data? Okay, TMDB data is a movie ID. It's a dictionary where looking up a movie ID will lead to a TMDB ID string and also a poster file name. So in the application, the poster file name is the TMDB. So that copy link address, I guess. Well, yeah, copy. So, okay, the poster file name is this part. The image, they have different images of different width. So this is a 342 pixel version of the image. So that's the poster part. The ID is the 154. So when I click on the link, it's this one. So it's actually, when I click on the link, it's actually this. And then they redirect it to the Star Trek 2 URL. So the ID is this one, the TMDB ID. To get this data, so these data are obtained by downloading from the TMDB website, and to do that you need to get an API key, so which I can't blur out here. So before using this script, before using the download TMDB data script, get the API key. The API key is free. You have to register as a developer, and the API key is free, so it's rate limited to 1 API calls per second. So my code has a pause time of 2 seconds. There's a 2-second pause between TMDB API calls to satisfy the rate limit. So now I have put the ID back into the script, and now I can run it. and it's going to download, one movie every 2 seconds. The full data set has 58,000 movies, so this could take a long time to download. So every 60 seconds, this script will save whatever data it has to disk. And if I terminate it just by Control C and restart it, it's going to start off at movie ID 26, where it last stopped, because it's reloading the data from disk and continuing on. So that's how the download can be completed. I don't expect people to have their computer open for like a few days to download all this stuff. Just press Control C and then, after saving the data to disk, and then resume the download later on. So there's actually if you run this for long enough, there's actually 2 files being saved to disk. Data. So one file is the TMDB data file that has the actual data, and there's also a bad ID file. So these are the IDs where I don't get a response from the TMDB website server, so that when I resume, I don't retry the bad IDs over again, because over time there's a lot of bad IDs, and retrying the bad IDs at 2 seconds per movie, that would take up a lot of time. So that's how you get the TMDB data file and the title search index files. Now all of these files I have included in the app local directory. All the important files, all the files that are necessary to run the application is in that directory, because actually deploying this to Amazon AWS and setting up a website, that's a lot of work. So I want to make it easier for people to run the project. So if you want to, you can get the TMDB data file and title search and movie and similar movies and whatever from that directory if you want to. But in this presentation, I've shown how to get those files, how to build those files.